Hello everybody, we're broadcasting live from my kitchen here about 10:15 p.m. Finally got everybody to bed so we could make a video. This is number 2 from your MyMathLab pre-class assignment, at least my version of number 2. It starts out giving us S in the UV plane is this square. Basically unit square, right? 0, 0 to 1, 0 to 0, 1 to 1, 1 out here. And we want to do the thing that we did in class, which is translate each one of these 4 boundaries into new boundaries on the XY plane. Ignore this, I messed up on one of my parabolas over here, so we'll come back to a better picture in a moment. The equations that I have here are x is 2u squared minus 2v squared, and y is minus 4uv. So on this bound, what's going to happen, so if we take boundary 1, down here v is 0 and u goes from 0 to 1. So v is going to disappear here. You just get 2u squared running from 0 to 1. And over here you just get y is 0. So if we think about what that is, basically we're just letting u run 0 to 1 for 2u squared. That's just going to draw out the line segment out to 2. So it's just going to go from 0, 0 to 2, 0. So on my improved picture over here, you can see boundary number 1 is just this little line segment right here. Let's move on to boundary 2, which was this boundary. Over here, we have a u value constantly at 1 and a v value that changes from 0 to 1. So we do our conversions again with these equations. X is 2u squared minus 2v squared, and y is minus 4uv. So when we convert those, here we get x is 2 minus 2v squared, and y is minus 4v. So we get points of this form. 2 minus 2v squared is 4v. Well, I want to change those into xy coordinates, so I'm going to solve this second one for y. So y is 4v. I'm going to solve that for v. v is y over 4. And then I'll plug that in over there. And now I get x in terms of y to be 2 minus y squared over 8. Well, that actually gives me an equation then. X is 2 minus y squared over 8. I can plug that in and find out that this is the parabola. Y squared is 16 minus 8x. So that is a parabola, a horizontal parabola instead of a vertical parabola. And actually, if we go ahead and graph that one, you can see it here. It goes through 0, 4 and 0, minus 4. And it also touches out here at 2, 0. So that is boundary number 2. Okay. Now let's move on to boundary 3. For boundary 3, we had v was 1 all the time, and u is running 0 to 1. So you can see that here, v is always 1, u is running from 0 to 1. So that one's going to work similarly to the last one. X is 2u squared minus 2, y is minus 4u. We do the same thing where we're going to solve for u and plug in. And what we end up here is in a very similar situation. We can set x to be y squared over 8 minus 2, so y squared is 8x plus 16. So we have another horizontal parabola. This one for boundary 3 is over here and opening to the right, goes through the same points at the top and the bottom. It's just mirrored over here. The last edge that we have is u is 0 and v goes 0 to 1. You can see that edge here. U is always 0, v goes 0 to 1. If you work that one out, this is similar to the first one. X is minus 2v squared, so that's going to run 0 to negative 2. Y is always 0, so this is this line segment right here. So we've got our boundaries. Now the question is it this area up here or this area down here? Well, a little bit of looking back at the original. We were up here, and u and v are both strictly positive up there. So if you think about our substitution down here, our y values are going to be 0 or negative. I guess this isn't strictly positive, it's 0 or positive, right? So this is going to be 0 or less all the time. So we actually need the region down here, right? Because all of our y values are going to be 0 or negative. So that is our new region. Another way that you could do that would be just try some points that were in here and see where they map to, right? So for example, if you took 1/2 that was in there, you could see where that went to in x-y coordinates. Of course, you can see the y coordinates can be negative, which tells you I need this region down here. Okay, let's move on to MyMathLab problem number 6. This problem actually asks us to go through the entire process. We're going to integrate over a region R minus xy dA, and R is the square in the xy plane with these coordinates 0, 0, 2, 2, 4, 0, and 2, negative 2. But we want to do this with the transformation x equals u plus v, y equals u minus v. Now admittedly, this thing is not the hardest thing to integrate as it sits, right? We've done much more difficult things. We could split this. We could just integrate. Well, actually, we could split this way, and we could find the area at the top. You could actually just do this with geometry, right? This is not the most difficult thing in the world. But we're going to do a transformation here. So the first part is to sketch this in x, y, and uv. Well, there's the x, y. That's pretty easy. We could do the thing that we did before where we label all the boundaries and look at the equations and move things around, but everything's linear over here. This is a linear transformation, and one of the facts about linear transformations is that they transform lines into lines, which basically tells us we can just look at where the 4 vertices go and map to 4 new vertices. So all that I did here was take for x, y, 0, 0, I plugged into my 2 well, actually first I had to solve this to get equations for u and v. I added them together to get that x plus y was 2u, so u is x plus y over 2, and x minus y is 2v, so v is x minus y over 2. This is kind of a common trick that we use. So anyway, then if you plug in 0, 0, you get 0 for u, 0 for v, and so on. This is how I got the rest of my points, and you can see basically what our transformation did is it untilted our square, made it straight over here. Okay, for part B, we're supposed to decide what the bounds are on the UV plane. Well, that's pretty simple. It's 0 to 2, 0 to 2. For part C, we're supposed to do the Jacobian. I actually set it up kind of backwards, trying to do the Jacobian like we did today at first. I left the answer there on purpose. This is the Jacobian that we need to do. Partial x respect to u, partial y respect to u, partial x respect to v, partial y respect to v. And you can see that's going back to these. These are pretty straightforward, right? You're just going to get 1s or minus 1s out of all those partial derivatives. So you end up with minus 1 is minus 2. Now when I set this up backwards, I actually ended up with minus 1/2. This is going to happen, right? These are always going to be reciprocals of each other. I think that might come up in a problem where you're supposed to find this Jacobian value, but they give you the transformation backwards. Well, sometimes it's a little bit of a pain to do this process that I did to solve for u and v or whatever the variables are. You can do the transformation or the Jacobian backwards and just take the reciprocal. That will work. Okay, for part D, we are actually supposed to integrate. Well, I need to change my variables. So this is u plus v, u minus v, so it's u squared minus v squared, but then we have a minus sign, so it's v squared minus u squared, du dv. And actually, we also need the Jacobian stuck in there. And our Jacobian value was minus 2. So when we're done with this, we have to multiply, I'm just going to pull that out here actually, by negative 2. It doesn't end up mattering on this one because this integral, when you work it out, going through step by step here, integrate with respect to u, you get uv squared minus u cubed over 3 plug in the 2, you end up with 2v squared minus 8/3 dv. Integrate again, you get 2v cubed over 3 minus 8/3 v. Plug in the 2, you get 16/3 minus 16/3 is 0. And then yes, we're supposed to do -2 times that, but it's 0, so it doesn't really matter. Okay, that is it for examples for this section. I hope those are helpful, and I will see you in class.